Hello everybody, my name is Michael Kinney. I'm with Intel, and I've been involved in UEFI firmware since about 1999, and am one of the EDK II maintainers and stewards on the TianoCore site for the open source implementation of UEFI. And in the past year, or most of this year, I've been really focused on some of the Capsule update elements and making big improvements to that. So today I'm going to talk to you about those improvements we've made in the EDK II implementation to use UEFI Capsules to update not only system firmware, but platforms composed of many other devices, subsystems that may also have firmware loads in them, that you want to be able to update those independently of your system firmware, or even potentially update your system firmware as a set of individual components as well. So that's some of the things we've been working on this year, so I'll go through some of those details. Okay, I'll go back. So. The first thing is one of the things we're also wanting to stress with some of our Capsule update work for firmware is to make use of push servers for getting the firmware content out into the target systems. So in this case, we've been looking at the Linux Vendor Firmware Service as one of the ways to distribute firmware content. The development process we go through here is we start with the work we do on firmware, whether it's for UEFI firmware or other firmware payloads that are in your platform. You have to generate a UEFI capsule that contains that firmware payload. Once you've got what you think is a good capsule with a validated set of firmware content, you would then go through step 2, which is to publish that UEFI capsule to a service like LVFS. And then from that service, it would then be distributed down to the set of target systems that support that UEFI capsule, and those UEFI capsules will then be processed on that set of target platforms to update the firmware for that component. So for the talk today, we're mostly focused on what does it mean to process those capsules. So I'll go through some of those details and what does it take to actually implement in your UEFI firmware side the support needed to actually do that processing and update of your firmware storage device for your firmware payload. And then we'll also talk briefly about the capsule generation side and some of the improvements we've made on that aspect as well. So looking at this picture, which is one of the standard pictures from the platform initialization specification about how a system boots and the various phases, and we'll go over this as far as what it means when we're processing a capsule through these various boot phases of EDK II firmware. It starts with the security phase, and then the PEI phase where basic platform initialization occurs, silicon initialization occurs, then on to the Dixie environment, whose job is to produce the standard set of UEFI services, and also provide some of the I/O subsystems for booting your platform. Go on into a boot manager. From there you can do things like run some diagnostics, test the shell, but you can also, more importantly, run your bootloader for your operating system, and then get up into the runtime where you're actually booting an operating system and able to run some applications. So if we look at this same picture from the perspective of Capsule update, there's a number of things that happen. The first one is we're doing a normal boot and we get all the way up into the operating system from the end user's perspective. And from there, they'll be running some service that may ping something like the LVFS server for, do you have updates for my platform? And if it finds any up there, the LVFS server will send those down to the target platform. And what happens while the OS is running is those set of capsules are saved temporarily off to the side. And once a number of capsules have been downloaded, maybe one, maybe more, eventually there'll be a reset system that occurs, and then it'll do a normal boot again. And that normal boot, it'll only come up to the part where the bootloader runs. The bootloader will run, and it'll look at the set of capsules that may have potentially been saved to the disk at OS runtime on the previous boot. If there are capsules there, it'll go through each one of those and will call the UEFI service called update capsule. That'll send the capsule and stage the capsule in memory in most cases, and then after all those capsules have been processed and staged in memory through the update capsule service, it'll do a reset system. The platform knows capsules have now been staged in memory, and it will boot in a special mode called boot on flash update. So the platform knows that there's capsules queued there. It'll come up through the PEI phase, and one of the interesting aspects of capsules in the update capsule service is that if you're running at OS runtime with Capsule update, the pages, physical pages associated with the capsule can be scattered all over memory. And as a result, when we get to the PEI phase and we need to bring the platform firmware up, we tend to need some linear chunks of memory in order to complete the platform initialization. So we have to walk through a scatter-gather list provided with the capsules to coalesce the memory associated with the capsules so that all the capsules are in a linear chunk of memory, and then that frees up memory so it's not checkerboarded, so we have enough memory to complete the boot of the platform. So we have those coalesced capsules come up on that boot on flash update path, and we get up to the processing of capsules in the Dixie phase there, right before what's called end of Dixie. It's actually implemented in the BDS module just before you get to the end of Dixie. And we process capsules. We know we're in boot on flash update. There may be a list of capsules. We process each one of those. And that's where a capsule has a GUID associated with it that uniquely identifies the device to be updated. And it can do a match between that capsule and a firmware management protocol that's present in the system. If it finds that match, it forwards that capsule to the firmware management protocol. And that's where the capsule is processed and potentially a flash device or firmware storage device is updated based upon the capsule contents. If many capsules are sent through at a single boot, then all of those capsules are processed, many different subsystems are updated, and in the end, they're all completed, and it resets the system again. And then it comes up through a normal boot now using those new firmware images, gets all the way up into the OS runtime, and once again, now we're running at a point where something like LVFS-related services can then verify where the capsules it staged on the top line actually, when we got done with that whole capsule update process. There's a special table called the EFI System Resource Table, which advertises the set of updatable components and their versions, and if an update was performed, it provides status on that update. Was it successful? Did it fail? Did it update to the right version that was expected? So the OS agent can then verify that it actually occurred correctly, and if there were issues, it can then have remediation paths that are handled from the OS agent side to see if it needs to retry a capsule if there was a failure, or if everything's good, it can then go on and do normal OS activities and wait for some future time when more updates are maybe available from the LVFS service. So that's the basic flow. The next set of the talk is really about that process UEFI capsules and what happens, what do you have to actually do in your code that you implement in the UEFI firmware in EDK II to actually write to your flash device and update it in a secure, safe, robust manner. So here's where that set image call there in number 1 is what happens when we process a single UEFI capsule. We have the UEFI capsule image in memory. It's been coalesced back in the PEI phase, so it's all in a linear buffer. Call into the FMP driver, which is producing the firmware management protocol, and we call the set image service with that UEFI capsule being passed in. The FMP driver in the firmware management protocol, its responsibility is to authenticate that capsule. If the capsule is corrupted in any way, it doesn't look like a UEFI capsule header, it doesn't have the proper FMP header, or if it actually does the signature verification based upon a set of public keys that it has, if that auth fails, all those things are going to cause the capsule to be rejected. It's really important that you only apply capsules to a platform or a device that it actually applies to, so we do a number of extra checks all through here to make sure it's really correct. If it passes all of those checks, we then know that we have a valid payload in memory that's been authenticated, and we can send that on to the one function that's actually going to write that payload into the firmware storage device. So that's step 3 to do the update. And whether or not you're in a boot on flash update path or a normal boot path, every single boot, the FMP driver, when it runs, advertises a GUID into the ESRT table, so we always have an inventory of the updatable components advertised on up into the operating system environment on the platform. And that same ESRT GUID is the one that was also used to match the capsule with this specific driver instance, so we're calling the right FMP protocol. So that one GUID you'll see through the presentation travels through the whole system in several places. So, as I said, my work this year has been mostly about making big improvements to simplify what it takes to actually implement support for that last action of processing a capsule and updating your firmware storage device with the new capsule contents. Capsules are not new. Support for capsules in the EDK II is not new. It's been there since UDK 2017 with a fairly good implementation. But what's happened in August of this year, we had an EDK II stable tag that was dropped on the TianoCore EDK II repository, and it contains a number of feature improvements to the way that Capsule update occurs. First of all, there's now a standalone tool for generating capsules. It used to be completely integrated inside of the EDK II build environment, which meant if you were trying to do a capsule for something that had nothing to do with EDK II, you still had to use the EDK II build environment and all of its syntax for setting that up in order to build a capsule for a non-EDK II firmware component. So that was a bit clumsy. Now we have standalone tools, whether or not you're doing EDK II based firmware load or a non-EDK II firmware load, you now have a standalone Python script that can help build those capsules for you. The other thing is that the previous implementations were really focused on monolithic updates. Send me one capsule per platform, and it'll update all of the firmware devices in the entire platform. This new one is about really supporting and trying to encourage the use of component update. If you have independent subsystems in your platform, you want to update them independently. Now we have full support for that, and it was really designed with that use mode. The other thing that we found is that we had some requests from customers to support multiple keys per capsule. So they have use cases where maybe during validation, formal validation, they want to use one key for formal validation and a different key for actual formal release. So that the content's the same, but they just have one extra different signing action they do between those two. So the single key limitation was actually problematic, and so we've extended it to support as many keys as you need for your environment on your platform. The other thing that wasn't there by default was some of the pre-checks you want to do before you apply a capsule. Is your platform healthy enough to actually support doing a capsule update right now such that the capsule update can complete without issues? Is your battery in a good state? Are you connected to power or not? Are the thermals good in your platform? If any of those pre-checks fail, maybe you don't want to do the capsule now, reject it and come back later once your system has the right attributes to support a capsule update. Some of the other things we've added is there's a consistent user experience now when a capsule is being updated and the flash device is actually, or firmware storage device is actually being updated. It presents a nice screen that's consistent, but there's also options if you have a different platform that can't support like a graphical console or text console, you can customize that with your own kind of progress indicator to the end user. Before that required a platform-specific implementation. Now we have a standard way to snap in those standard ways of showing the user that there's a firmware update going on in the platform. And probably the biggest one is really around the Firmware Management Protocol itself. You had to do a complete implementation of that whole protocol. We've now simplified that whole process down to give us some data values associated with your firmware update and implement a small library, and we've taken care of all the rest of the code for you. So your amount of work you have to do to implement firmware update for an individual device or component is now much less. Some other things we've moved into some built-in features or things around a test key detection. Watchdog timer is built in. In addition, we've simplified the publication of that ESRT table with the inventory of updatable components. There was some history here of ESRT was actually defined before the Firmware Management Protocol was added to the UEFI specs, so it had some legacy ways to put entries into the ESRT table. Now that we're consolidating all firmware updates around the Firmware Management Protocol, those legacy methods don't make sense anymore, so we've been able to reduce a little code and a little boot time by stripping out some of those old features. So I mentioned the firmware update indicators. There's two built-in libraries that we have. If you have a GOP, graphics output protocol, in your platform and you want to do a graphical console, then you'll get a picture like the left where you can have your system logo that shows up somewhere on the display. Underneath it, as a firmware update is occurring, there'll be a progress bar that's rendered, and as the progress indicator is updated from 0 to 100%, it'll actually show a colored bar, and you can customize the color of that bar for each one of your devices. In addition, there is a specification from Microsoft, a public one, about a user experience bitmap, and what they mean by that is it's an opportunity for the operating system agent that's sending capsules down to send one additional capsule that contains a bitmap, and that can get drawn at the bottom of the display, and it can say something like, please wait, your system is updating some firmware right now. don't turn the power off. But they can also do that in a localized language because the operating system knows what locale the OS is installed for, and they can now send down a generic bitmap that gets displayed at the bottom of the screen. And then the picture on the right is if you only have a text console, there's a basic implementation of the same progress bar concept, and it uses some colors if possible based upon the 16 foreground colors that are available in a PC-NZ-like text console, and can show progress of different components being updated. And as I mentioned before, if you have a device that doesn't have either one of these consoles, maybe something like an LED can be flashed appropriately or some audio tones, you can do a custom version of the display update progress lib to indicate to the user that an update's occurring. Even for something like a small LCD panel or something like that could maybe have some indicators on that you do as a custom implementation. So I mentioned that we simplified what it takes to implement the Firmware Management Protocol. All the boxes in blue are code that's in the EDK II that you should just use as is, no changes. So we have a wrapper driver for producing the Firmware Management Protocol. It takes care of the authentication of the UEFI capsule for you. You don't have to write any code to do that. And the only two things that you do have to provide are potentially the platform vendor-specific library that does the system environment pre-checks. Is the battery, thermal, system good for a firmware update? And the other one is the FmpDevicePkg, and that's the one that each device vendor that has a separate firmware storage device, that's the set of APIs they'll go implement to actually do the update to the storage device with the already validated payload. And I won't spend a lot of time on these because I think the slides will be available, but this is the idea. I said there's two ways that you provide some information about your firmware update. One is through a set of data values, and we call this the platform configuration database, is the EDK II nomenclature for providing some data values for configuration. So you can provide some information about your GUID that you're using for your device. That's the unique identifier for your device that's updatable, along with the name of your device, a Unicode string, so it can be named correctly out of the Firmware Management Protocol, as well as when do you want to lock your flash device down. Typically that's at the end of Dixie, but a platform may choose a different lock point for all their firmware storage devices. If you're arming a watchdog, how many seconds does the watchdog get rearmed each time a progress update occurs on the progress bar? And then finally, the most important one is really this one right here, which is what are your set of public keys that you're using to validate your capsule? So you provide those in a PCD as well. So once again, no code to write, you just provide a data value with your certificate in there. And we actually have a tool that if you're using something like the OpenSSL command line tools to create your certificates, we have a simple tool you can use to convert that binary file or set of binary files if you're doing multiple keys into a PCD statement that you just bang include into your DSC file. And so no cut or paste or errors that can occur in that developer process. And then the last one is if you want to disable test key detection, there's a simple way to do that as well. Test key detection's on by default, and then you can disable it if you want to save some boot time. If you're doing the platform-specific work around power, thermal, and environment, this is the one library class you'd implement. There's 3 APIs around system checks. There's 2 additional APIs there that's really around a service mode or manufacturing mode. So if you want to have a way to prevent your flash devices from being locked or allow an older version of firmware to run, you can basically put some hardware-specific, platform-specific checks in to say, I know I'm in a service center, or I know I'm on the manufacturing line, and I can allow some different policies to occur. By default, these are implemented as false and false. It's like, no, I'm not in those environments. I'm actually out in an end-user state, and do not leave the flash devices unlocked. And this is the most important one. This is the set of APIs you have to implement per device. The ones with the bold italics there about the currently stored firmware image, most of these APIs are really small and simple to implement, just a couple lines of code. Our preference, and to make it easier, it's better if you lay out your payload that gets stored in the flash device such that you can always extract out of the stored firmware image things like its version string, and that kind of information. Also be able to extract the image out pull the image out of the firmware device itself. The one API that is the biggest, the most complicated, is this one final one, that is the FmpDevicePkg image. That's the one where you'll actually write to the firmware storage device, and you're passed in a progress API that you're asked to periodically call between a value of 0 and 100% as you work through your update of your firmware storage device, and so that you can get that progress indicator updated on the display. So it's typically erase a block of flash, write the next block of flash, and then update the progress to the approximate percentage that you've gone through your flash device for that firmware component that you're updating. And that's where the majority of work's done in this library. There's a couple of use cases now around when you have multiple updatable components in a platform. Here's your system firmware. You've got multiple FMP drivers, so this is showing 4 updatable components in the platform. You have an ESRT table with 4 entries, so that advertises up to the operating system. There's 4 updatable components. And importantly here is really around the key management. You get a choice to where you store your keys. You can store them within the driver itself because it's a PCD element. You can choose the patchable and module type. It's inside of the driver. Or if you want to put it inside of some vital product data area that's a protected area of your flash, you can choose to store it there as well if you want to have shared keys amongst multiple updatable components. So a full platform that has full control over all of their updatable components and signs them all with the same key may choose the vital product data area. If you're integrating components from other parties, you may be choosing the picture of the items on the right where the keys are actually inside of the driver themselves. It all depends on who signs the keys and who validates. Now when we get to third parties, here's an example where if you have a third-party vendor that's producing a device that has firmware on it that can be updated, they can produce a firmware driver, an FMP driver, that you can integrate into your system firmware as is. And one of the things you might want to do is actually replace the keys that are there from the third party with your system keys, because you don't want to allow the third party to produce a new capsule that automatically gets installed onto your platform without you doing some verification first. So by replacing the keys with your system keys, what you're saying is, I'm not letting that third party into my platform. By default, I'm going to validate first, and if I validate their new capsule, I will resign their capsule, and then I will publish a new capsule available for my platform signed with my keys, such that then my end users will get that firmware update. So that's one model where the system vendor has full control over every firmware update to every component in their platform. There's another model here where if we keep the third-party keys there, that's the mode where if a third party then produces a new capsule and publishes it on LVFS, as an example, then all the platforms that have that device in their system that's signed with that third-party key, that's advertised with that same GUID, they'll start receiving that update that that third party produced. So that's a second model that a platform vendor can choose to take advantage of. And another mode that's available is if you have an existing device driver you've already implemented or another vendor's implemented, and it does have firmware update as a possibility, but they haven't implemented it yet, there's a way to use the exact same code that I showed as a separate module and just link it in as a library into your existing device driver. It's actually the exact same code for us in the EDK II. It's 2 different INFs, one that's advertised as a library, one that's as a module, but they function identically, and you do the same work. You set the PCDs in the scope of that module, you write your one library, that FmpDeviceLib, and that will just fold in and work for you. So in summary, the EDK II, it supports this new set of capsule features that really simplifies what it takes to implement Firmware Management Protocol for devices, and really trying to encourage this idea of supporting not just monolithic update for platforms as most are today, but let's work on splitting it out to multiple updates, different update for each component. Added support for multiple authentication keys, added the support for pre-checks to make sure the system is compatible with doing a firmware update right now. That more consistent user experience while a firmware update is occurring with the progress bars. And the support for the test key detection and the simplified ESRT table based only on the Firmware Management Protocol. We have the new tool called GenerateCapsule.py, which is a way that independent of the EDK II build system, you can build capsules for any kind of firmware component, whether they're EDK II based or not. One of the methods we have for publishing and distributing UEFI capsules is to go through things like the Linux Vendor Firmware Services for those platforms that have that firmware update manager service able to run, or the GNOME software able to run on that target. They can then see those updates on the LVFS server and automatically download and install those. So the call to action here is go implement using the new FmpDevicePkg as described here. Do it for your system firmware, and if you have other devices in your platform, go start implementing those FMP drivers or work with those third-party vendors to have them help work on the FMP drivers for their devices. Take advantage of the features I listed here, and take advantage of the LVFS as a way to distribute your capsules, and provide feedback and contribute to both the LVFS project and to the TianoCore EDK II. The kind of our future work that we're looking at past this is this scope of effort is really focused on your platform, your system firmware, and integrated devices. When you get to things like adding cards, like PCI adding cards, and doing firmware update to those, or to other kinds of devices outside that, that's some of the work items that we're still looking at to make that as simple as possible as well. So that's some of the areas that we like to collaborate with the community on getting those problems solved as well. So that's the end of the presentation. I'm available for questions.
I think you're out of time, actually. But I don't see you over here. Oh, yeah, you go.
There's a microphone there.
I was just saying, I think you're out of time, so we should have time for a quick question, but then we should give the floor to Hongbao to...
When we update, compare with Windows and Linux system, and Linux will automatically do the update, or need to manually initiate?
So with the LVFS project, it will automatically send it down and automatically do the updates. It has that capability. So really between Windows update for Microsoft operating systems and LVFS for Linux systems, they're kind of peers. They work the same way. And there's actually been some great work by the LVFS team to make it so that it's possible to build a capsule content that you can send to the Linux portal for signing and distribution through LVFS, and send that exact same capsule, no changes to the Windows one. So that's they've done some great work to make sure that they're compatible. So from the vendor's perspective, that's creating the capsules, they do their work once and then just publish through two portals.
I think I looked at this capsule stuff, and one thing I thought I saw missing was, do the capsules have versioning information, major, minor versioning, so that if I'm doing a system firmware update, I can tag that and say, I want to know what it is. And then secondly, when I copy such a capsule to the /boot partition that you guys talk about in your spec, can I make sure that the file name includes the version number or something?
So yes, the ESRT table and capsules all have 32-bit version values in them. They also have lowest supported version values to have like security boundaries you can't go below. So that's all in there. And as far as the format on disk, for UEFI capsule update using update capsule service, there's no disk file associated with it. There is a feature in the UEFI spec called UEFI capsule on disk, and that one is not implemented in the EDK II yet. So that's one of our future work items that we're working on. Okay, thank you.